In an extended panel, the neutral and grounding wires are separated onto different buses to prevent electrical shock hazards and arcing faults. The grounding wire, which is green or bare copper, provides a low resistance path for fault current to return to the source. The neutral wire, which is white, carries the imbalance current from the loads back to the source. When these wires are separated, it prevents neutral currents from flowing on the grounding system. This prevents overloading the grounding conductors and creating safety hazards. The National Electrical Code, or NEC, defines accessible as applied to equipment as admitting close approach and not guarded by locked doors, elevation, or other effective means. This means that equipment must be within reach and not obstructed by barriers or enclosures. In the context of breaker panels, the highest breaker should be no higher than 6 foot 7 inches so that it can be easily accessed and operated. The formula power equals voltage times current, or P equals E times I, is used to calculate power in watts. P stands for power in watts, E represents voltage in volts, and I represents current in amps. To determine the wattage a 14-2 NB wire can handle, given it is rated for 600 volts and 15 amps, you perform the calculation power equals 600 volts times 15 amps, which equals 9000 volt amps. However, wire capacity is not solely determined by the voltage rating marked on the wire's jacket. The ampacity, or current carrying capacity, of a conductor is limited by its size, insulation type, and the ambient temperature it operates in, as specified by the NEC. The voltage rating on the wire, such as 600 volts, indicates the maximum voltage the wire can safely handle, not its ampacity. For a 14-gauge wire, such as 14-2 NB, used in typical residential wiring, the NEC generally limits the overcurrent protection to 15 amps, regardless of the wire's voltage rating. The most common mistake is calculating a higher wattage based on the 600 volts rating, but the limiting factor is the ampacity. Therefore, although the wire is marked 600 volts, its capacity is determined by the 15 amp limit. You should refer to NEC Table 310.15b16 or consult with a qualified electrician to determine the appropriate ampacity for the specific wiring conditions. The appropriate power calculation for a 14-gauge wire protected by a 15-amp breaker is therefore power equals voltage times current, which equals 120 volts times 15 amps, which equals 1800 watts in a typical 120-volt circuit. In a 240-volt circuit, it would be 240 volts times 15 amps, which equals 3600 watts. So, a 14-2 NB wire with a 15 amp breaker in a 120 volt circuit can handle 1800 watts. The value of 1600 watts is not directly derived from a simple calculation or a standard NEC table. It might be a conservative estimate, a rule of thumb used in certain contexts, or a specific requirement in a particular jurisdiction. It's important to verify the source of that number to understand its relevance. To summarize, firstly, separate neutral and ground wires in subpanels to prevent dangerous current flow. Secondly, ensure breakers are accessible as defined by the NEC. Thirdly, correctly calculate wire capacity using the appropriate voltage and current limits. Firstly, understand the importance of separating neutral and ground wires in subpanels to maintain safety and prevent electrical hazard. Secondly, be aware of the NEC definition of accessibility, ensuring that breakers are within reach and not obstructed. Thirdly, calculate wire capacity correctly by using the appropriate voltage for the circuit and the ampacity of the wire as determined by the NEC, rather than solely relying on the wire's voltage rating. The ampacity of a wire depends on several factors, including its gauge, insulation type, and the ambient temperature. The National Electrical Code provides tables, such as Table 310.15b16, that specify the allowable ampacities for different types of conductors under various conditions. Always consult these tables to determine the appropriate ampacity for a given wire in a specific application. The voltage rating of a wire indicates the maximum voltage that the wire can safely handle, but it does not determine the wire's ampacity. A wire with a higher voltage rating does not necessarily have a higher ampacity. For example, a 14-gauge wire might be rated for 600 volts, but its ampacity is typically limited to 15 amps when used in typical residential wiring. When calculating power, it is essential to use the correct voltage for the circuit. In a 120-volt circuit, use 120 volts in the power calculation. In a 240-volt circuit, use 240 volts. For example, a 14-gauge wire protected by a 15-amp breaker in a 120-volt circuit can handle a maximum of 120 volts times 15 amps equals 1800 watts. In a 240-volt circuit, the same wire and breaker can handle a maximum of 240 volts times 15 amps equals 3600 watts. Local codes and regulations might impose additional requirements or restrictions on wire ampacities. Always consult with a qualified electrician and local authorities to ensure compliance with all applicable codes. Overloading a wire can lead to overheating, insulation damage, and potentially fire hazards. It is crucial to select the appropriate wire size and overcurrent protection device to prevent overloading and ensure electrical safety. Regularly inspect electrical wiring and equipment for signs of damage or deterioration. Replace any damaged or worn wires and components promptly. Consider factors such as ambient temperature, conduit fill, and dirting factors when determining the appropriate wire size and ampacity for a specific installation. These factors can affect the heat dissipation of the wire and reduce its allowable ampacity. When in doubt, always consult with a qualified electrician to ensure that the electrical wiring is safe and compliant with all applicable codes and regulations. Always disconnect power before working on electrical circuits or equipment. Use appropriate personal protective equipment, such as insulated gloves and safety glasses, when working with electricity. Follow lockout/tagout procedures to prevent accidental energization of circuits during maintenance or repair work. Test circuits with a reliable voltage tester before touching any wires or components. Never work on live circuits unless absolutely necessary, and only do so if you are qualified and have taken all necessary safety precautions. Keep electrical panels and equipment clear of obstructions to ensure easy access for maintenance and repairs. Label circuits clearly and accurately to facilitate troubleshooting and prevent accidental disconnection of critical loads. Use properly sized and rated overcurrent protection devices to protect circuits from overloads and short circuits. Regularly inspect overcurrent protection devices to ensure that they are functioning correctly. Install ground fault circuit interrupters, or GFCIs, in areas where electrical equipment is likely to come into contact with water, such as bathrooms, kitchens, and outdoor locations. GFCIs can quickly detect ground faults and interrupt the circuit to prevent electrical shock. Follow manufacturer's instructions for installation, operation, and maintenance of electrical equipment. Use only approved and listed electrical equipment and materials. Do not attempt to repair or modify electrical equipment unless you are qualified to do so. Keep electrical cords and cables in good condition and avoid overloading them. Use surge protectors to protect sensitive electronic equipment from voltage spikes and surges. Educate yourself and others about electrical safety practices.